My name is Andrew Guillory. My summer research project was on Fragmented Brightest cluster galaxies, and my advisor was Dr. Ming Sun of the UAH Physics and Astronomy Department. So we're going to start off with a quick introduction of what brightest cluster galaxies are, or BCGs. And as the name suggests, they're the brightest galaxies within a given galaxy cluster. And they're also the most massive galaxies that we know of. What we are trying to look for is what we're calling fragmented brightest cluster galaxies, which are the same idea as a BCG, just multiple components. These can be very important as they can give insight into early universe formations, black hole mergers, and potential interactions with dark matter. A little bit of background before we get into what I actually did for my project. There's already been a lot of research done on BCGs themselves. There's been little actual research on how they came to form, but there has been a lot of research on how galaxies themselves form. BCGs themselves have also been very useful due to they're very useful for using for deep sky observations and measuring deep space distances, as well as observing behaviors of massive black holes within their centers. What we hope to do is that if we can kind of get an idea, if we can find enough candidates of fragmented BCGs, then we can get quote unquote snapshots of different stages of these large galaxies merging together to become a bigger galaxy. So what we did for this project was more of a preliminary step to try and be able to set up a standard classification and find some potential candidates for fragmented BCGs. So the main tools and programs that we used for this project are listed here. These are the main ones we used. We used other stuff such as Excel and Google spreadsheets to be able to move data along as well. The main astronomical databases that we used was Sloan Digital Sky Survey, or SDSS, and NASA Extragalactic Database, or NED. From NED, we pulled galaxy cluster samples, and then cross-referencing that with Sloan, we were able to search within those galaxy clusters to be able to find these denser groups of galaxies that we're calling fragmented BCGs. The main thing we used within SDSS was called cache jobs, and that works through a search language called SQL, or structured query language. This was a big learning curve for me to be able to use this to be able to parse through massive tables within the database itself. After we used cache jobs and SQL to get data, we would use other programs to parse through the data and find different groups, so that way they might be reliable. So and these codes were typically written in Python or C++. So that was kind of our process I kind of described there. This is going a bit more in depth into it. Using SQL in cache jobs, we were able to parse through the data by cross-referencing data from SDSS and NED. The parameters that we used was typically the galaxies had to be within 25 kiloparsecs of each other, which is big, but still relatively close together in the grand scheme of things. We also said that they had to be within a certain brightness magnitude, and we also used various flags within SDSS to filter out contamination points, as we ran into a lot of problems with that. Once we had all the data from cache jobs, again, as I said, we used Python and C++ to parse through them to find groups within them. We then analyzed the groups, and then we had to attempt to find redshift data on our more reliable candidates, so that way we can confirm that these galaxies are actually close to each other in relative space. And the picture on here is actually of some code that I did. This is an example of SQL, and this was mostly what I was working with and looking at throughout the summer. I wasn't really looking at pictures or taking pictures. In fact, all the pictures on here were pulled from Sloan or some other source just on Google. So again, these pictures are from Sloan on this one. So our key findings and some conclusions that we were able to draw. The big thing that we noticed very early on was that we had groups of 2 to 4 were very, very common. And so we wanted to refine our search to find more extreme examples of groups possibly between 5 and 10. 5 to 7 or 8 we found were pretty common. We would still get hundreds and hundreds of groups of 2 to 4 before we found a group bigger than that. But finding groups of 5 to 8 were pretty common, and then finding groups of 10 were pretty rare. So we decided to try and focus on those bigger groups so that way we could take extreme examples and then maybe narrow it down to the smaller examples later on. And the 2 pictures here are kind of opposite ends of the spectrum. The one on the right is an example of one of the more extreme examples. This one has a potential 11 candidates within it, and this was one of our best ones that we had found. The one on the left only has around 4 or 5. So the one on the left was something that we saw a lot more common. The one on the right was something that we were looking for more, but didn't find as many of. And this project was a continuation of a project that I also worked on last summer, but we were able to identify and fix a lot of the problems that we were having last summer, so that way we could get more reliable data this summer and progress. So again, this project was more of a preliminary step to start building this classification. It's difficult to make sure we had all the information and everything, so that way we could start doing this, but we plan for a lot more research in the future, whether I'm doing it or another undergraduate student picks it up. Our plans originally at the beginning of the summer were to start doing quantitative analysis or physical analysis on the groups at the end of the summer, so that way we could start to kind of apply some of those ideas I had talked about at the beginning. Unfortunately, we didn't get to that. We had some time constraints and other complications that we had to sort through. So we're hoping in the future to begin with analysis as part of future projects. We also want to refine the classification a bit more and hopefully find some more extreme candidates like I had shown in the last slide. And that's about it for the actual project. Before I finish this video, I do want to say a special thanks to David Cook and Dr. Vogler for putting on this program this summer, because I know this was very difficult, especially with everything for COVID-19. So doing everything online was very difficult for everybody, and I know that they had a lot of trouble, but they did a great job. So thank you to them. Thank you to the UAH Office of Provost and the Office of the Vice President for Research and Economic Development for the support and funding. And another thanks as well to the speakers and volunteers that talked about special topics for us to be able to grow as researchers and students. So that was my project. Thank you for listening, and stay safe.